start off. Clean data is not actually a technical term. So one of the questions that we have is what are the characteristics of clean data? What are we talking about when I talk about clean data here? Basically, what I'm shooting for with clean data is data that is well structured, that's going to be easy to use in a variety of software. I want data that once I've archived it, it's going to be easy to take out of the archive and have somebody use it. To a certain extent, we're also talking about data that is as free of errors as we can possibly do, but I know we're going to be having a second session that really focuses on sort of the QAQC aspects of things, the quality control and assurance and fixing those. So I'll touch on it here, but I won't go into it sort of a great deal. Now, first question, why archive data? Okay, this is one of the XKCD webcomics here that says it's unsettling to realize how quickly digital resources can disappear without ongoing work to maintain them. So we see that, you know, books have been there in the past and they'll be there in the future. Web databases, maybe not so reliable. Maybe you can depend on archive.org to capture them, maybe not. But all of them sort of reflect the fact that digital data is inherently limited in terms of its sort of archival qualities. And especially if you're dealing with data that is linked to one particular software product, you're going to have a particular time. As the webcomic says at one point, it's Java front end no longer runs. And not too long ago, I actually was trying to pull up some data, and it turned out that it only ran under MS-DOS, the software that would allow me to access it. So I had to stand up a FreeDOS machine to get at it. Anyway, so we want to make it as easy as possible to use that data in the future. So I'll start off with, is this true? That data that's ready for analysis or presentation is ready for archiving? Well, I would argue that that's not the case. That analysis-ready data can be archive-ready, but most often it's not. The data that's ready for analysis or presentation often is taking complex forms. It's sort of human-readable. It's, you know, it's designed to look attractive, but those may not be things that make it sort of easy for a machine to use it. What we want for archiving data is we want simple forms. We want to be consistent, and you're going to hear the word consistent a lot today because that's sort of the key to clean data in this framework. We want it to be as generic as possible, unlinked from any software product if we can possibly make it that way. Let's start off with the ugly spreadsheet. This is not actually a spreadsheet that somebody gave me, but I have received spreadsheets like this. This is just about everything that could be done wrong has been done wrong on this spreadsheet. Take a look at it and see if you can spot where the problems might be. I don't know if you want, we can talk about it during the questions, or if somebody wants to jump in, but in this case here, you should be able to spot some issues. The big thing is inconsistency. Okay, sometimes we've got in line 2 up there in column E, we've got the word date plus the date actually stuffed into one column. Whereas in line 7, we've got the date in column F, while the label is now got its own little cell. Just about all of the labels for each of the types of measurements that we're making, and these would be basically 2 dates where you went out and made measurements with a water quality using a conductivity probe situation and salinity. And so what you see is that the same things have been measured both times, but the names are different, the ordering in the table is different. Like I say, inconsistency. We also don't have similar codes. And also we've got all sorts of symbols mixed in with our numbers. We've got less thans and percents, all sorts of things there that are going to cause us problems later. This is a spreadsheet that is a little bit better, but it's still pretty bad. In this case here, we at least don't have a bunch of mini tables. We do have some columns out there, but we've got a bunch of omitted values there. Okay. For a person, this actually can be helpful. It basically means that you can easily spot when one date is stopped and a new date is started. But in terms of the computer, it basically means that, lines 3 through 7 have no dates. We don't know, the computer doesn't know what dates those are. Heaven forfend that we should ever sort this file. If we sorted it, we would completely lose the ability to know the dates on things. Another place where there's inconsistencies, we've got the tide state there. Well, we've got very inconsistent codes. The numbers 1 through 7 there, or 2 through 7, lines 2 through 7, all have essentially the same tide, sort of slack high tide. But sometimes it's slack dash high, sometimes it's slack underscore, sometimes it's uppercase, sometimes you just plain run the two words together. Well, for a person, you look at it and you go, okay, I understand those are the same thing. But for a computer that is going to be more precise in its thinking, getting those so that they line up is going to be a major problem. And then sort of the last thing that I want to point out is that we've got all sorts of places on here of where we have data that are not numbers in columns where everything else is supposed to be numbers. If I wanted to look at the average of the salinity at the bottom, what is the average of 1 and 3.2 and greater than 35? How do you deal with that? Not to mention the fact that if you were to read this sheet into R using the default read.csv function, it would take a look at that salinity bottom column and say, oh, okay, that's a text column, and basically would treat even the numbers as if they were letters. So that top cell would be the letters 0, period, and 6, not the number 0.6. So we want to make it so that those columns are as consistent as possible, and that means not mixing text and numbers together. Now we'll talk a little bit later, if you'd like, about just how we can deal with that situation where we do have uncertainties associated with particular measurements, of where our measurement limit was exceeded there or something like that. There are some best practices that are out there. That one of my favorites is one that came out from Ecological Bulletin in 2001, and it basically talks about the fact that data formats should be consistent over time. So you don't want to have it every time you go in and collect new data. You don't want to have a new format for that data. So that means that we want to be adding rows to our data set, but not adding new columns. Similarly, the columns of data, again, be consistent. You shouldn't be mixing those different things together. So for archiving, again, we want to have complete lines of data. It means that every line's got its date. We want consistency. Every code is the same as every other code, for the matching conditions, and that every column's got one kind of data in it. If you can stick with those rules, your life will be just so much easier. I'd imagine that as we get into the question part of this thing, that each of you maybe has a data set that you've encountered that just sends chills down your spine. I know I've got a couple of them, and I'll be actually showing you one in a second. Actually, we'll show it to you right now. Okay, this was actually a real data set. I'm not going to say who collected it, but it looks spectacular in the spreadsheet. Okay, we're going to focus on the headers part, not the data part per se. It looked great in the spreadsheet. Up at the top there, we see the all of the business of the. Oops, let's see. I was trying to pull up a highlighter, but let's see if it does it here. Okay, laser pointer. Here we go. Yeah, here we go. So up here, this is what it looked like in the spreadsheet. Looked absolutely great. We've got two different locations, a creek bank and a low marsh. Those have 3 replicate samples, A, B, and C within them, and then each of those are replicated twice with the lowercase a and b. Looked great on the screen, but when I convert that into a CSV file in the middle here, you can see it's just a disaster. And then if we go and we read that data back in, convert it back into an Excel file, what we get is this one down here. And the problem is that what we've done is we've lost that Excel formatting. CreekBank no longer extends over all 3 of these. If we want to see what site C is in there, we've got no clue. And we've got 3 columns here that are, well, actually 6 columns that are simply labeled B. You know, how are we going to discriminate those apart? So ultimately, what I had to do was to go back and collapse those 3 vertical levels into just a simple code that would all fit on one line. So this has got CAA would be Creek Bank, Transect A, Replicate A. So when this particular data set came in, I had this for like about 10 years worth of stuff to deal with. And so it was an absolute nightmare. I was cutting and pasting spreadsheets. I didn't mention that this data also came with these little mini tables all scattered together in one spreadsheet. So you'd be done with one table and another would start halfway down the spreadsheet. Anyway, still sends chills down my spine to think about this data set. I'll talk about how I dealt with it for the long term in a moment. The other thing also that's useful is to have some good names up at the top of the columns. These are sort of a set of rules I like to go with. One of them is to avoid spaces and special characters. So in some computer languages, having something that's got a pound at the end of it may have special meaning. Similarly, computers are not really good at recognizing that things that are separated by spaces really belong together. So I would avoid that sort of thing. Having mathematical operators in your column names is a really bad idea. Here we've actually got a division operator in there. And that's would be interpreted as by a program that might be trying to use this data as actually trying to do a division operation. So generally speaking, I recommend not ever using any special characters in there. The other thing also is start off your, do not start your column names off with numbers. The reason is computer programs tend to be incredibly lazy. They don't bother to read a whole thing in order to see whether it's a number or a string. Sometimes what they do is they just look at the first thing and they say, oh, that's a string, so I should, or that's a number, I shouldn't be using that as a variable name. It's also not a bad idea, since the number of characters that different programs allow you to use as a variable names, so they've gotten a lot better in recent years, is to make it so that the front part of your column name is something that is sort of unique and distinctive, that even if you truncated off the rest of it, it would still work there. So I've got my little example down at the bottom. This one, pretty much every one of these labels has violated things in some way. I've got a mathematical operation there. I've got lots of spaces there. I've got my symbols. I've got a percent signs. I've got a subscripted number there. All of those things are going to cause trouble when you go to different software. So instead, you want those clean ones of where you're got underscores for the spaces, and you're not using any of the special symbols there. Now, the truth be told, you should also be able to store all of the units in a longer variable name, something that really provides the detailed description with as many spaces and as many special characters as you want in the metadata as sort of the label for this column, but it shouldn't be the thing that's at the top of the column. That's stuff that belongs in metadata, not actually in the data file. It is nice to have something, though, that's a little descriptive. I mean, in principle, we could just say V1, V2, V3, V4, V5. That would fit with all of my rules, but we'd sort of like to have it of where we have some clue just by looking at it as to what they are. Another question that comes up is, how should you take and have a separate data file for perhaps each site or for each year, or is it better to sort of combine them together? And I tend to be a lumper, because when it comes to describing a file in metadata, I'm going to have to describe the file. Well, if I've got 10 files, then I have to describe 10 files. If I've got one file, I only have to describe one file. And especially if the columns are the same in all of these sort of individual files or in the main one, that's a very strong case for combining them. Only if there were substantial differences in which columns needed to be in these files would I say they should be separated. The other thing also is, in most software, it is relatively easy to select out say that we only want site 1. Well, even in Excel, I can take my all sites 1, sort by site, and then just delete all of the other sites in just a few minutes. So it's usually easier to select all of the things. Sometimes it can be fairly difficult to actually do the combining later using things like Excel. Excel's not super great on merge operations and that sort of thing. Missing values. Yeah, this is a big challenge, because one of the things is that different software packages have different ways that they like to indicate missing values, and often those ways are mutually contradictory. If you are working with SAS, well, it wants to have a letter indicate a missing value. On the other hand, if you put a letter into a column and R or SPSS are reading it, they're going to consider that that column is all text. And so you'll have to convert everything back into numbers. Either that or throw errors about the fact that that's there. SPSS would like to have you put some sort of an impossible numeric value that you would then identify as its way of doing missing values. R really likes you to use the letters NA as a missing value indicator. MATLAB may use not a number. Sometimes you just leave a null or a blank space. Lots of different ways to do it, and each one of them will work with some things and not with other things. Probably the ones that are the safest are things like leaving it blank. Although in some cases, the software will then say, oh, it's a blank space, this is a column of numbers, they must have a 0 in there. So when you go to do the average of that column, all of a sudden it's a lot lower than you thought it was going to be. So you need to track those. And SAS also likes just to put a period in a column that's got empty values. The other danger with blank space is that sometimes they're sort of hard to see whether they're there or not. In spreadsheets, not too bad. In other things, it could be more difficult. Yeah, this is sort of the problem. I'll let you look at that for a moment. And at this point, we're at least at the 15 standard stage and maybe above in terms of missing values. So let's look at a sort of a summary of what we've talked about for the best practices for data structure. Again, the word consistency. comes to mind. We've got good descriptive columns. They're stable columns. We're not going to be adding or deleting columns as we add new data. We've got we're going to be using good missing value codes, and we might use data flags. We'll talk about data flags in just a moment. And since I've only got one data table here, I've only got one data table that I need to document. I don't need to document 50 different data tables. Now, sometimes you want to transform the data. Obviously, if you have data like our ugly data table that consists of sort of little mini data tables, one over top of the other, those you probably want to reform. But another type of data that you often want to deal with is ones where you're doing sort of survey data. So what we've got here is we've got a plot that we went to on a particular date, and then we've got a list of species abbreviations across the, starting in column C and heading out, and then we've got the number of individuals of each of those species that we observed, and this would extend outwards. Now the problem comes in what the heck happens if we have a new species. I mean, we've done some good things. Each column has only one kind of data. We've got some really nice labels up there. But if we need a new species to be added, what we've got to do is add a new column. And remember, we talked about the fact that we would like to have it that when we add new data, we only add lines and not columns. So how can we restructure this data so that we no longer have that situation? One way to do it is to basically go from our wide format here, where we have all of the species names going out to the side, to something where instead what we now have is a variable that's going to indicate which species this cover value applies to. Now, one of the things about this structure is if you do have lots of cases of, in this case here, for our little example here, we've got examples of, or individuals of each species in each of the plots, but we might have situations of where most of the species are not in plots. And so we have a tremendous number of zeros in our data. With this long format here, we no longer have to have the zeros. If we want to put them there, we can, but we don't have to have them there. And so now if we're going to add a new species, well then we just have to add a new code to our list of codes for the species column, and we're good to go. These columns will work just fine for us for any number of species that we might have put in there. Now this switching between wide and long is sort of increasingly easy to do. R and tidyr both have some good routines for doing that with gather and separate and spread can be very powerful on that, and even the reshape command in the base R can do this. Similarly, you can do this in spreadsheets with pivot tables, but don't ask me how. I have not done that in a long time. And by the way, you can also easily convert anything that was converted into the long format can be easily converted back into the wide format as well. Quality assurance and control, QAQC. Well, at our site, we get data from a number of different sources. We have our individual researchers. They're mostly going to be giving me data in spreadsheets. We have our technicians. More and more, we're having the technicians actually use a database management system for their input of data. We have our automated sensors. They're going to be coming in their own formats and then are processed using statistical packages into the form that we'd like to have them. And then we've got a set of web forms for doing metadata. And then we've got GIS systems for dealing with the spatial data. But the ones I'm going to focus on right now are the issue of the spreadsheets, because spreadsheets, I almost have a hate-hate relationship with them. I contend that spreadsheets are so flexible that they not only sort of allow bad practice, but in some cases, due to the way the routines are set up for doing plotting and things like that, they actually encourage bad practice. But there are tools in the common spreadsheets that actually can be very good for you if you know they're there and if you know how to use them. So let's take a look at one of those. How many people knew that if you went up into Excel and clicked on data, you can go down and there's data validation? So for this column, air temp, I can go say that air temp should be a decimal number. I'm going to ignore blank ones. I'm going to allow you to not fill it in. And the data value should fall between 0 and 35. If you try to put in 36, it's going to do something. And that doing something is set over here under the error alert and on the input message, so that you can either make it so that it says, no, that's greater than 35, I absolutely won't take it. Or you can have something pop up that says, this number is higher than we would really expect. You know, you're welcome to enter it, but please make sure that it's correct. So that's a very useful thing to have. Another capability that's particularly valuable is the one where you can define. Notice that in this particular spreadsheet, I've got a couple of different worksheets here. I've got the field data, which is what we're seeing here, but I also have one that's called metadata. And in that one, then what I will have is a list of all of the codes for things like the tide state, or all of the codes that are for the station names. And with this same data validation, you can, for text values, actually say, hey, you need to pick a value that's included in this list from this metadata sheet. So that means that somebody can't mistype something, or at least not do it easily. They can use pull down lists. And it also means that you've got sort of a consistent result out of it. Now, unfortunately, I would say that probably, well, easily 80 to 90% of my colleagues that use spreadsheets don't know about these features, and so they don't use them. But that's not to say that this can't be a very valuable tool. Now, for some data sets, it's just too complex for a spreadsheet. We have some data sets of where we'll be, well, let's take a look at one. This is one of the databases that I set up for one of our technicians for collecting data for field sampling. So we'll periodically be doing a collection. So this will just be, we'll be going out on, in this case, June 10th, 2014. And then you can list who was going out there. And then on that particular day, you visit a number of sites. And so we've got a section here that lets you set what the site is. And then within that site, you might encounter several different species. So we've got a block for that. And then for a given species at a given site during a given collection, we then can have a length of a fish, and then also how many of them were that length, so that if we got 20 of them that are the same size, we can record that there. And then once I've recorded the lengths for that species, I can hit new species, click on the next species that I want to add data for. And this one basically enforces everything so that nobody can make a mistake in terms of the species codes and things like this. When we were trying to do this in a spreadsheet, we ended up with sort of all sorts of problems like that. And so this further constrains people. Now, the downside of doing this sort of thing is that this takes a long time to set up. You have to do a little more training with the people on using it. it's also possible to do some bad things. Like, for instance, if I went down here and changed that from length 70 to length 700, well, then boom, it's in the database. There's no saving and that sort of thing. So I have mixed feelings about it. If anybody has any better tools for data entry, let me know, because I don't think that the book has been fully written on that. Now, aside from sort of the enforcing of conditions or checks, we can also go out there and do additional checks. This is sort of that quality control and quality assurance sorts of things. Some of the things are relatively easy to do. Some of them can be very sophisticated. Once you start doing things like comparisons with nearby stations or trying to detect sensor drift, those are tough things to do. Others are really easy. I mean, you can look to see whether a date is valid or not. That's the calendar is pretty well defined. If somebody has added a 13th month, well then, by gosh, that something needs to be done about that. Also, graphics are not to be laughed at when it comes to sort of doing additional checks. This is one. Can you spot the problem sensor there? Yep, that's the Brinson 3 well there had a bit of a problem. This is looking at the battery voltage for the well, and it turns out that a deer had gotten its antlers tangled in a wire and ripped it out. So we're slowly discharging our way down to nothing. I do think it's interesting that over about a 2-week period, though, we still only dropped about 0.6 of a volt, which says something about how little power Campbell data loggers use. Anyway, I would recommend taking a look at this paper that some of us put together a couple of years ago that basically sort of details a lot of the types of quality checks and things that can be done. We talked a little earlier about the fact that sometimes there are qualifiers about data that we would like to put into the data so that we know that maybe we exceeded the measurement range of an instrument. In other words, it was greater than 35 parts per thousand, but our instrument only went up to 35. And for those, typically the best practice is to use data flags. This is a separate column. It's not the data itself, but it's a column that allows us to provide essentially metadata on an observation by observation level, so that we can literally go through and say, for any particular number in the table, this is the this is what was wrong with it. This is why I don't trust it. This is, maybe it says that I'm absolutely sure this was right. But it's basically a place where we can put additional metadata about it. Now, the one thing is that I would like to be able to tell you that there was a standard set of flags out there that were ready for you to use, but they tend to be a bit on the esoteric side. Now, some of you may be able to sort of inform me on if you found some good listings of that, but they often are a tricky business. And I know that that sometimes it's nice also if you can get to that level of certainty about your uncertainty to actually give, say I'm 80% certain about this data or 20% certain, and then that lets the user make some sort of determination about their sort of comfort threshold for data risk. So looking at sort of the whole process there. A lot of what we're dealing with initially is that level 0. That's where having our data input set up so that it does good checking is a valuable thing. When we go to process that data, that's where we can do some additional quality checks, maybe merging the new data with the old data, making sure that we've eliminated any duplicate observations, all of the sort of routine things you should do when you do that. This is where we can get more into our advanced quality assurance. If we're going to be doing things like comparing across stations, this is something that you can do there. And then sometimes we will get this level 2 data here. At this point here, a lot of the steps that are in here, like gap filling, synchronizing, aggregating, downsampling or upsampling, changing the time period so that they match up, all of those sorts of things typically involve sort of some scientific insight. You need to have somebody there who is really knowledgeable about that data and knows sort of what makes sense in terms of what you're doing there. It's things like if you're adjusting water pressure sensors for atmospheric pressure, and you only have atmospheric pressure once an hour, but your well data or your pressure sensor data is once every 10 minutes. Well, do you then need to aggregate all of your water pressure data to once an hour? Or if you realize that the air pressure typically doesn't change very much in an entire hour, you're then maybe okay to interpolate the air pressure and keep your higher temporal resolution on the sensors. So like I say, when you get to this level 2, you're talking about sort of doing a lot of real scientific work there. So usually what we're trying to do for our archival things is to get things to good quality level 1 data and do it there. Well, I sort of left definitely some time for questions there, so I will throw things open. What would people like to ask me? Feel free to jump in. If somebody wants to share war stories about the worst data set they've ever seen, I'm more than open to that. I bet you guys have seen some corkers.
Kristen, okay.
Can you hear me, John?
Yeah.
Okay. This is sort of tangentially related, but I have a PI who wants to archive sociological data. It's a bunch of interviews, apparently. And I'm wondering what your recommendation is for how to organize that kind of data.
Yeah, we've done that sort of thing too, because this is another one of where the number of columns can get to be incredibly high, because if you've got 50 questions and a column for each question, then they just keep going and going and going. Now, one of the things about it is that it depends a little bit on whether, well, the 2 ways you can do it is you can do it sort of the wide way, and you can also do it the long way. Sort of you can, let's see. Again, we can do it the wide or the long way. And then if you're doing it the long way, then what you have is simply the column D there would be the response to a particular question, and column C would indicate which question that was. Now that has the advantage that it's relatively compact, but it assumes that the answers to your questions are comparable, in the sense of like where we've got cover here. This is always a number that goes between 0 and 100. If this was a multiple choice type of response thing where they were giving 1 to 5, well then this might be a very reasonable way to do it. If there's a large sort of block of text, or if the form of the answers differs sort of wildly, then you may want to stick with sort of the wide format. Now, the other question also is whether or not this is a questionnaire that's going to be used again, and are you going to want to combine the data from one round of the questionnaire with the other round of the questionnaire. If that's the case, then since you can never count on them not adding questions or subtracting questions, that again sort of argues for using the narrow format, because you don't have to, again, adding a different question just would be similar to adding a different species in this example. You wouldn't have to go and add a new column for a different question. Now, One of the things I also do, though, is that a lot of times the people that will be using data are very similar to the people that are creating it. A social scientist is the most likely candidate to be using the data there. And so one of the options is to ask the person or ask other social scientists what they think they would like the data to look like, and then try to match that up. You know, keeping, again, as long as it's consistent, you can get by with a lot of things, but it's the inconsistent stuff that really kills you. Now, one of the things that's also a possibility for your test data there, especially if we're talking sort of long text responses, is actually putting it in an XML file might not be a bad way to go. In other words, basically having an XML file where you have a question element, and within that question element, you've got the question, you've got the response, and you've got, you know, whatever other information might need to sort of go along with that. And then archive that along with a documentation of the schema, so that anybody who wanted to use it could very easily run it through a style sheet and get it in whatever form they wanted. Anyway, but I have to confess, we do not have any XML data sets on our site at this point.
Thank you very much.
Hi, John. This is Tim Whitaker. How are you?
What can I do you for?
I was wondering, how much of these best practices do you give to your PIs or your investigators beforehand versus working with them after the fact to clean up their data?
I definitely have things on my website that are videos or PowerPoints with narration that are very similar to this presentation here. But it's a very tough row to hoe. Some of these investigators sort of learned how to use spreadsheets years and years ago, and they have their own ways about doing them. So they're a little bit hard to pry away from it. But I'm seeing a lot of hope in the graduate students, not necessarily because they're learning better practices in terms of spreadsheets, but because more and more of them are learning things like statistical packages like R. And if you are using R and you're used to data tables, well, a data table more or less is that sort of consistent, column-oriented format. And so for them, it's not such a stretch to do it. I will confess that even though when I get a data set that is relatively clean in terms of having good columns and things like that, there are still often problems in terms of the names that they might have used for the particular columns, or things like that you require just sort of a little tweaking to sort of make them better. And in some cases, I will actually go to the trouble of actually converting things from wide format to narrow format, but that's a little bit more of a heavy lift there. Did that sort of get at your question?
Yeah, thanks.
Yeah, but I believe me, I've tried the training part of it, and it's really hard when their major professor says, "Oh yeah, this is the way you do it." The other thing also that I might add also, and Kristen would really be the one who could best address this, is that just as I said that data that's ready for presentation is not necessarily data that's ready for archiving, the form of data that is ready for archiving is not always the best form for data input or collection. So you might very well want to have a clipboard that you take out that's got the species names all across the top, and then you just find the right block and fill it in when you're collecting the data. But that may not be the way that you want the data to be archived. So each sort of place might have its own little different form of the data that would be the ideal one.